For 28 years, 4 different space telescopes tried to do one specific thing, and every single one of them failed. Astronomers had been picking up a faint signal from the Pluto system since 1997. The problem was that nobody could tell which of the 2 objects it was coming from. Pluto and its giant moon Charon sit so close together in our sky that their heat signatures blur into a single smear of light. It's the astronomical equivalent of trying to figure out which of 2 people standing shoulder to shoulder is talking from a mile away in the dark. This year, that 28-year problem finally broke, and the answer it revealed is stranger than the mystery itself. Pluto and Charon aren't really a planet and a moon in the usual sense. Charon is more than half the size of Pluto, and the 2 of them orbit a shared point of gravity that sits outside Pluto entirely, the closest thing our solar system has to a double planet. From Earth, roughly 3 billion miles away, that whole system occupies a speck of sky so small that separating the 2 objects thermally requires a telescope with extraordinary resolving power. Europe's Infrared Space Observatory tried in 1997. NASA's Spitzer Space Telescope tried in 2004. The Herschel Space Observatory tried in 2012. All 3 caught something. None of them could cleanly separate Pluto's contribution from Charon's. The signal stayed tangled for a quarter of a century. Here's why untangling it is actually important. In July 2015, after a 9.5-year journey across the solar system, NASA's New Horizons spacecraft passed within 12,500 kilometers of Pluto's surface, closer than the distance from New York to Mumbai, moving at roughly 14 kilometers per second. It was the fastest and first close look humanity had ever gotten at Pluto, and the data it sent back didn't match expectations. Pluto's upper atmosphere was measured at around 30 degrees Celsius colder than standard atmospheric models predicted it should be. Gas alone couldn't explain the deficit. Something else was pulling heat out of the system. The flyby also revealed why. New Horizons cameras caught something nobody had planned for: a towering blue-tinted haze layered in more than a dozen distinct bands, reaching over 200 kilometers above Pluto's surface. It was made of tiny organic particles, not unlike the haze that shrouds Saturn's moon Titan, coated in thin films of frozen hydrocarbons. It was beautiful. It was also, at the time, assumed to be cosmetic, a visual feature, not something that could meaningfully affect Pluto's climate. In 2017, a planetary scientist at UC Santa Cruz named Xi Zhang looked at the temperature discrepancy and proposed something that broke from that assumption entirely. What if the haze wasn't just floating there? What if it was actively running Pluto's thermostat, absorbing sunlight by day, radiating that energy back out as infrared heat by night, and in the process, cooling the atmosphere far more efficiently than the surrounding gas ever could on its own? It was, by Zhang's own later admission, a bit of a leap. On every other atmosphere we'd studied, Venus, Mars, Titan, the gas giants, the energy budget is handled by gas molecules, not suspended solid particles. The idea that a haze layer could take over as the dominant control mechanism for an entire planet's temperature didn't fit anything in the existing textbook. Plenty of scientists were openly skeptical, but Zhang's hypothesis came with a built-in test. If haze particles really were cooling Pluto this aggressively, they should be radiating a specific, detectable signature in mid-infrared light. Prove that signature exists, cleanly separated from Charon's own heat glow sitting right next door, and the crazy idea becomes confirmed physics. Fail to separate it, and the idea stays exactly what it had always been: untestable. That's the 28-year problem again. And it's exactly the problem the James Webb Space Telescope was built to solve. JWST's mid-infrared instrument, MIRI, was designed to work in precisely the wavelength range where Zhang's predicted haze signal should live, and with a large enough mirror and steady enough pointing to finally resolve Pluto and Charon as 2 separate thermal sources, rather than one smeared blob. In May 2023, JWST captured a mid-infrared spectrum of the Pluto-Charon system spanning roughly 5 to 27 micrometers. For the first time since anyone had started looking in 1997, scientists could measure Pluto's and Charon's thermal emission independently. The results, published by Tanguy Bertrand and an international team in Nature Astronomy on June 2, 2025, with Zhang and his former student Linfeng Wan contributing the theoretical modeling to interpret what the telescope was seeing, confirmed the 8-year-old prediction almost exactly. Pluto's haze particles really are absorbing and radiating energy fast enough to dominate the atmosphere's heat balance, holding the upper atmosphere colder than gas-only physics would ever produce on its own. Bertrand's own description of what this makes Pluto a new kind of climate, not a variation on something we've cataloged before. Something we haven't seen operate this way anywhere else in the solar system. Sit with that comparison for a second. We have detailed atmospheric data on Venus's runaway greenhouse effect, Mars's thin carbon dioxide shell, Titan's thick nitrogen haze, the crushing hydrogen envelopes of Jupiter and Saturn. Every one of them is fundamentally a gas-driven system. Pluto, a world so small and cold it was stripped of its planet status in 2006, is apparently running on physics none of the bigger, more important worlds use at all. And the story doesn't stop at Pluto's own atmosphere, because some of what's escaping it isn't staying there. JWST's data shows Pluto continuously losing atmosphere to space, methane bleeding away at roughly a kilogram or so per second, nitrogen escaping more slowly alongside it. A portion of that escaping methane doesn't just vanish into the solar wind. Models suggest a slice of it, on the order of a few percent, actually gets captured by Charon's gravity and drifts down onto its poles, where the extreme cold locks it in place. Once trapped there, ultraviolet light and cosmic rays go to work on it, breaking the methane apart and reassembling it into reddish organic compounds called tholins. This mechanism, Pluto essentially bleeding atmosphere onto its own moon and staining its poles in the process, was first proposed from New Horizons-era modeling to explain Charon's mysterious red polar cap, informally nicknamed Mordor Macula. JWST's newer data adds real weight and detail to that picture, on a moon that has no atmosphere of its own to generate that color any other way. It's a genuinely strange relationship. Charon isn't just orbiting Pluto. In a very literal sense, it's being painted by it. So why does any of this matter beyond one small, distant world nobody's spacecraft will visit again for decades? Because haze-dominated atmospheres aren't unique to Pluto in principle. They might just be unique to Pluto in our own solar system. Exoplanet surveys have already picked up thick, opaque hazes on sub-Neptune and super-Earth-sized worlds orbiting other stars, and right now, our climate models for those planets are built mostly on the gas-driven physics we know from home. If a haze layer really can seize control of an entire planet's energy balance the way Zhang predicted, and JWST just confirmed on Pluto, then some of those distant, haze-wrapped worlds might be running on the same rulebook, which means our current models for reading their atmospheres could be missing the single most important variable in the room. There's an even stranger possible echo of this closer to home. Before oxygen reshaped Earth's atmosphere roughly 2.5 billion years ago, our own planet may have been wrapped in a haze of organic particles, produced by very different chemistry, but not entirely unlike what's floating above Pluto today. If haze particles can meaningfully stabilize a planet's temperature and drive its chemistry the way they appear to on Pluto, that raises a real, open question about whether a similar mechanism helped keep the young Earth warm and chemically active enough for life to eventually take hold. A frozen, 3 billion mile away dwarf planet, demoted from full planetary status less than 2 decades ago, may be quietly holding a working model for the kind of atmosphere that helped make life possible here. That's not a stretch dressed up for drama. It's the actual reasoning researchers are now pursuing, precisely because Pluto turned out to be running physics nothing else nearby uses. None of this was supposed to be visible. 28 years of failed attempts to split one faint signal into two had turned this into something close to a known limitation of ground and space-based infrared astronomy, a problem you filed away and revisited only when the next generation of hardware showed up. JWST didn't just clear that bar, it cleared it well enough to confirm a hypothesis that had been sitting untested for the better part of a decade, in a world most people had already mentally filed as small, cold, and finished being interesting. It isn't finished. Researchers are already planning to point Webb at Neptune's large moon Triton next, checking for the same kind of mid-infrared excess that might mean a haze-driven climate is operating there too. And the Pluto data collected so far has only caught the early stages of a long polar winter settling in on its northern hemisphere, meaning the haze thermostat Bertrand and Zhang identified is going to keep getting tested, in real time, as Pluto creeps further along its 248-year orbit, and the sunlight it depends on keeps fading. Thank you for watching. I'll see you in the next one. Have a good day ahead.